Thanks everybody for coming and welcome to this talk about Big RAM. I'm going to talk about techniques that you can use for effectively and efficiently using large amounts of memory in the JVM. Just quickly, a brief introduction to myself. I'm over from London in the UK. I've been a Java developer for about 12 years now, and at the moment I work for a company called Cosata, and we make software that allows people to efficiently access large amounts of their customer data in real time, hence my interest in large amounts of memory. First of all, quick straw poll. Who's using more than a gigabyte of RAM on the heap in production? Most people, okay. 10 gigabytes? Quite a few people. 100 gigabytes? Couple, okay. Any more than that? 400? Okay, thank you. So, to start off, I'd like to make a very bold prediction. I believe it will be quite standard for server class machines to have more than a terabyte or multiple terabytes of RAM in, I'm going to say, 4 years' time. So, Java 1, 2016, we'll all come back here and I'll buy you a pint if this isn't the case. That's 1 pint between all of you, by the way, not one each. Now, I think there are a few factors that are driving this. The cost per megabyte of RAM has only halved since January 2009. So in January 2009, we could go out and we could buy 512 gigabytes of RAM for only about $5,000. Today, we can buy that for about $2,500. However, the difference is in 2009, it wasn't practical to do anything with this amount of RAM. You'd have lots of 2 gigabyte DIMMs. You could build some sort of Frankenstein machine to use all of this RAM, but you basically couldn't do anything with it in a single machine. The difference is now you can buy a server with 512 gigabytes of RAM for less than $30,000, and this price is coming down all the time. I haven't checked it in a couple of months, but it was about $30,000 a couple of months ago. And one of the factors driving this is the fact that the new generation of processors allows much more RAM to be addressed by the CPUs. So the new generation of Intel processors, which is Rumley, allows a maximum of 768 gigs of RAM in a 2-socket server. Previous generation only allowed 288. And again, next generation, probably a lot more, terabytes. Also, the other factor is that larger DIMM sizes are now quite cost effective. So a few years ago, I don't even know if you could buy 16 gig DIMMs, but if you could, they were very expensive. Now they're quite a reasonable price. 32 gigabyte DIMMs are still pretty expensive, but they're coming down all the time. So these two factors are really driving forward the increasing amounts of RAM in a server machine. So this presents us with some challenges. At Cosata, where I work, as I said, we have many, many terabytes of data, and all of this needs to be accessed in real time by our customers. Now, no matter how fast we make disk access and things like that, it's never fast enough. People always want their queries to return faster. People always want their analyses to happen faster. So we would like to improve the performance of our system by storing large amounts of data in memory. So what happened was back in March, our new CEO came to me and said, Neil, I've bought you a server. It's got 512 gigs of RAM. I want you to use all of this to make our application faster. And I said, sure, no problem. And I went and I set MX to 511 gigs. Why 511? I was giving the operating system some space to do its stuff. And I sat back and I looked at the results, and essentially this presentation is my journey from that point onwards. So, first thing we're going to talk about is garbage collection, as you might have expected. So when I got this server, I sat down and I created a little benchmark, which uses an LRU cache. It essentially shoves data in an LRU cache up to a certain size, and then hits that cache over and over again with about a 80 or 90% hit rate. I'm going to present some results from this benchmark in this presentation today. However, before I do, just a small word of warning. This is unlikely to be representative of your production environment. Your mileage may vary. So please do your own benchmarking and test this yourself, because my benchmark is unlikely to be what you will see in production. Brief note about the test hardware. As I said, 512 gigs of RAM, 32 cores, and what was at the time the latest build of the JDK 1.7. All of the tests I performed on the JVM were performed with, or all of the tests I'm about to show you, were performed with 10% of the heap free, so 90% live data in the heap. Now, some of you may be thinking, that's not really enough for the garbage collector to operate, and turns out you're right. So here's heap size on the x-axis versus garbage collection time on the y-axis for 3 different collectors. As you can see, with G1, with 400 gigs of 400 gigs of heap size, so that's 360 gigs of live data. We reach about 28 minutes for a garbage collection pause, and to be clear, that's a pause when the JVM is doing nothing apart from garbage collecting. So all your application threads are waiting there for 28 minutes. The reason why the line for the CMS collector stops at about 120 gigs is because I couldn't seem to allocate more than 120 when I was using the CMS collector. There is a bug for this that I raised, but it doesn't seem to be that high priority. I think that the plan going forward with Hotspot is to use G1 for all large heap situations. I don't think that fixing the CMS to work with large amounts of memory is a high priority, but perhaps somebody can correct me on that. Now, the times I've just shown you are worst case times, right? A lot of the time, the garbage collector will be able to perform concurrently to your application. The reason why I give the heap only 10% of free space is because I know that's not enough for the garbage collector to work concurrently. Thus, I was forcing a full GC. So this is really the worst case pause times that you'll see. However, there are various scenarios under which you can experience these worst case pause times, and I'll talk a little bit about that later. Now, there are some fundamental limitations to any garbage collected environment. If you allocate objects faster than the garbage collector can free them, then you're going to be in trouble. And this is specifically objects that are promoted to the old generation. You know, with large heaps, the assumption is that most of the heap is in the old generation, and so it's specifically tenured objects. That seems obvious, but it's worth stating. So what do we do about this? Well, we can leave plenty of free space in the heap. Now, I don't know about you, but when I have a 3 gigabyte heap, I have no problem with leaving 2 gigabytes free for the garbage collector to work in, 1 gigabyte of live data. I don't have any problem with that. However, for some reason, leaving 200 gigabytes free in a 300 gigabyte heap makes me uncomfortable. I don't know why. I can't help but thinking about all of that wasted memory. However, the ratio of free space to live data is the same in both of those cases. So you're really, in both of those cases, the amount of space you're giving the garbage collector to work in is identical. So you really do need to leave large amounts of space free in the JVM. Now, just to illustrate this point a little bit further, with any garbage collector that attempts to work concurrently to your application, there are going to be various trade-offs. So we trade off the proportion of heap used for live data, the object promotion rate, and the garbage collection rate. Let me just go through these in turn. So the proportion of heap used for live data is pretty obvious. That's the amount of data that isn't eligible for garbage collection. And the reason why this is important is that if you have a small amount of free space in your heap, which isn't used by live data, then you can only, then the garbage collector needs to have gone through and marked everything for collection in the time it takes to fill up that free space. So it's very important that you have enough free space in your heap. The other factor here is the object promotion rate. If you're promoting a large number of objects to the old generation, then the garbage collector has got to keep up with that object promotion rate. So again, that affects things. So if you increase your object promotion rate, you've got to decrease the proportion of heap that's used for live data. Likewise, if you increase your object promotion rate, you've got to try and increase your garbage collection rate as well. And that's the third thing. So the garbage collection rate is the rate at which we can actually collect or at least mark the data in the heap for collection. And again, that's important. If the garbage collector was able to collect everything very fast, then we wouldn't have to worry about having lots of space left in the heap. Now we can improve or rather we can decrease the object promotion rate by tweaking the size of the young generation. We can increase the garbage collection rate by assigning more cores to the garbage collector. And there may be other ways to speed up the garbage collector, but that's the simplest way, just give it more cores. And of course, the proportion of the heap used for live data can be decreased by increasing the heap size. Now, just to illustrate this a little bit further, here's the effect of free space in one of my benchmarks. So all of these tests were performed with a 120 gigabyte heap on the CMS collector. And you can see that things are ticking along quite happily, 50 gigs, 80 gigs of live data in the heap. As soon as we reach about, or at least when we reach about 110 gigs, we get a concurrent mode failure. You've probably all seen concurrent mode failures, because effectively the garbage collector isn't able to keep up with our object allocation rate, and all of a sudden we get a full GC, a pause, about 600 seconds. So even with plenty of free space in the heap, certainly in the hotspot collectors, there are situations in which long pauses or full garbage collections can occur. One example that's talked about a lot is defragmentation. So if your heap gets fragmented, the garbage collector has no choice but to pause and to defragment it. There may be other situations, but I won't go into those now. Just one final thing that you can do to improve the performance of your application with large heaps, make sure you've got explicit GC invokes concurrent enabled. So basically what this means is it uses the CMS collector when somebody invokes system GC, and you may be saying, well, nobody in my application invokes system GC, but unfortunately there are a few cases that are built into the JVM, like RMI and direct byte buffer allocation, which explicitly invokes system GC. And obviously you don't want this to bring down your entire JVM, so make sure you have that flag enabled. So I'm going to talk a little, I've talked so far about hotspot. I'm going to talk a little bit now about Azul Zing. So this is a commercial JVM with a so-called pauseless garbage collector called C4. It's not technically pauseless. Technically it has small pauses of the order of small numbers of milliseconds, but when you're coming from 28 minutes, that's effectively pauseless. So again, I ran the same benchmarks that I ran, that I showed you in the previous slide with Zing, and the results were pretty good actually. I showed pauses of about 100 milliseconds, so that's down from 15, 20 minutes. in my benchmarks, and this was up to about 230 gigs of live data in a 250 gig heap. Before Azul sue me, these pauses are not necessarily garbage collection related. They may be pauses to do with something else happening in the application. That's my disclaimer. It may not be GC related, but anyway, you know, it doesn't really matter. If you're going from minutes down to 100 milliseconds, hey, I don't really care. Now, the same limitations about object allocation apply with Zing. It's not magic. If you allocate objects at a faster rate than the garbage collector can keep up with, and you haven't got enough free space in your heap, then you'll get a pause in your application. Now, again, before Azul Zing sue me, this is not a garbage collection pause. Zing differentiates between garbage collection pauses and application pauses, but effectively what will happen is that your application will block on allocating memory. So it'll block on new. So, you know, there's no magic here. You still need to keep plenty of free space and watch your object allocation rate. So I did some tests versus hotspot with varying live data sets, a 250 gig heap. The results are here. Typically, I was getting pause times of tens of milliseconds with Zing, and with G1 and hotspot, I was getting hundreds of seconds, up to 1,000 seconds. Now, Zing managed to cope with live data set sizes of up to about 230 gigs in a 250 gig heap. However, this isn't necessarily a good condition under which to run. Essentially the less free space you have in your heap, the more you're going to waste CPU, because you can imagine that if you have very little free space, the garbage collector is going to be running continuously, you're going to get very frequent GC cycles, and you're going to burn a lot of CPU doing unnecessary garbage collection. So again, just a reminder there, Zing may be able to cope with, you know, large proportions of live data in the heap. That doesn't mean it's a good idea. Next. Just in case you thought that Zing was magic from their marketing literature, then here's some graphs. So this is Zing keeping up with my object promotion rate, which is about 15 megs a second. And as you can see, the amount of free space in the heap, which is the y-axis, is going up and down, but it's relatively stable. This is Zing not managing to keep up with my object allocation rate. And as you can see, the amount of free space in the heap is going steadily downwards because the collector is just not able to keep up with the amount of objects that I'm tenuring. And eventually the heap size reaches 0. In Zing, that doesn't actually stop you from allocating memory. It kind of reserves a big block of memory for its own uses, but that can't continue forever, and eventually you're going to run out and experience a pause. Just a quick word about throughput. I measured the throughput of my application, that is the amount of accesses I was able to do to my cache in Zing versus G1. Now, when the application was not paused, the G1 had higher throughput than Zing. However, taking into account the application pauses over a period of 1 hour, the overall throughput of G1 was about a third of Zing. So despite the fact that it was higher when it wasn't paused, it spent so much. It spent so much time paused that the throughput was much less. In general, my benchmarks seem to be particularly bad for G1. In general, the performance is much worse than I'd expect. With the amount of free space I was leaving in the heap for some of my tests, I would expect G1 to be able to perform concurrently. I'm not exactly sure what the problem is because I haven't spent any time trying to tune G1 yet, and unfortunately I missed the talk this morning. But yeah, I mean, this is sort of a caveat. It may be that we could tune G1 and get much better performance from it, but at the moment, in my benchmarks, it's untuned. So the next section of the talk deals with off-heap storage. So to overcome some of these limitations in JVMs, or in garbage collected environments that we've talked about, many people are starting to allocate memory off heap. So I'm just going to talk about this for a little bit. The most obvious way to allocate memory off heap is to use bytebuffer.allocate direct. And this essentially allocates memory in the JVM's process, but it's not part of the heap and it's not subject to garbage collection as such. You specify max direct memory size, you can just allocate off-heap memory happily for as long as you want. Now, this is only really useful for long-lived allocations, and here's why. Now, direct byte buffers, you can't free them explicitly. So they're freed by the garbage collection cycle. So you can get into a situation where, garbage collection hasn't run or it hasn't been running fast enough, and you've been allocating lots of direct byte buffers, and they haven't yet been freed by the garbage collection cycle. And so you come to allocate a direct byte buffer, and here's the code that executes. So it realizes it hasn't got enough direct byte buffer memory. So at least this code is from Hotspot. I don't know whether it's present in other JVMs. So whenever you try and reserve some memory for a direct byte buffer, it executes the system GC, which is obviously going to give you a very long pause. And then a thread.sleep for 100 milliseconds. I don't know why 100. It's clearly enough time for anything to happen in. It's undocumented. But anyway, so the point is that at some point, if you're allocating lots of direct byte buffers and freeing them over and over again, at some point you might get a nasty surprise when you try and allocate a direct byte buffer. So how do we get around this? Well, internally, direct byte buffers use a class called sun.misc.Unsafe and a method on there called allocate memory, which essentially lets us allocate a big block of memory off heap. And we can explicitly free this memory using the free memory method. Now, before I proceed, just a word of warning, you can cause all sorts of things to happen, all sorts of bad things to happen by using sun.misc.Unsafe. It's called unsafe for a reason, I suppose. But you can crash the JVM quite easily by using the methods in here, so just be careful. There's just, on the final point in this slide, I'm not going to cover this, but you can, in theory, move objects out of the heap into off-heap storage. There's an interesting blog post about this. This seems like a terrible idea because I have no idea what this is going to do to garbage collection, and this is beyond what I would probably consider at the moment. So here's a sort of sketch implementation of a wrapper object that allows us to store stuff off heap. Now we have to get a reference to unsafe using reflection. It's protected in some way in the JVM's jar file, so it can only be used by JVM internal stuff, but you can still get at it using reflection. I heard somebody mention at the Cassandra talk yesterday that they were thinking about bringing this into sort of more public access, which sounds good. To continue, here's my constructor of my OffHeap object. So field of the object stores the address that we've allocated memory at. We serialize our data. This passed into the constructor. I'm assuming I have some sort of serialization method that turns that into a byte array. I store the length of my byte array at my address, and then I write my data to an offset of that address. All fairly simple. Then to get that data back, I have a getter method. Excuse me. I first of all get the length of my data that I've stored in the memory location. I read that data from the offsets, and then I'm assuming I have some sort of deserialized method to turn that back into my actual object. Importantly, we have a deallocate method that frees up the memory that we've allocated that address, and obviously we need to be very sure to call that or we're going to experience a memory leak. I've seen people do things like reference counting with this, so you can always extend this implementation to provide reference counting and that sort of thing. Now, of course, there's a performance impact to using off-heap memory. As you've seen, everything must be serialized and deserialized when it's stored off-heap and when it's brought back into the heap. So there's clearly some overhead here. And not everything can be stored off-heap. I've given you an example of a wrapper object, and you're always going to have these wrapper objects. You need them to store references between objects. You need them to wrap the data that you're storing off-heap. And if you're storing your data in some data structure, that's probably on heap as well. So, for example, if you've got a cache, then you're probably going to have to store the implementation of the cache or the implementation of your map or whatever on heap. So you tend not to be able to store everything off heap with this technique. Again, my implementation is just a very quick and dirty implementation. There are many things that could be improved. For example, direct byte buffers do page alignment, so they align the allocations to memory pages for efficiency. Excuse me. Now, so I performed some tests of, again, same as my earlier tests. I had a big LRU cache that I was constantly adding to and evicting from. I stored a serialized linked list in here with a random size of between 1 and 140. And I had a live data set of about 320 gigs. Ran this test for about 6 days, creating about 3 megs a second. Now, the heap usage in this case was around about 90 gigs. So again, as I said, you can't store everything off heap with this technique. You've got to, in my case, I had a big map of keys, and the values were stored off heap. So I used about 25% of the total storage on heap. However, the maximum pause time was very good here. I was using the CMS collector. And my maximum pause time was less than 600 milliseconds. So this was with about 25% of free space in the heap. So about 120 gigs total heap size. And I didn't experience any long pauses at all. Everything was able to be collected concurrently. I think partly because I had some free space in the heap, but partly also because I was allocating less in the heap. And again, my process size remained stable over about 6 days. So this seems to indicate that fragmentation wasn't a problem here. I'll talk a little bit more about fragmentation in a minute. Throughput, as we might expect, throughput wasn't as good as with on-heap storage because, again, I've got this overhead of serializing and deserializing objects. So I got about 30,000 get input operations per second compared to about 160,000 for on-heap storage. So, it's not quite as good as on-heap storage. If you want a ready-made cache which uses off-heap storage, then I can recommend the Cassandra serializing cache. I mean, essentially, download the Cassandra jar, instantiate org Apache blah, 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 serializing cache, and you're off. You have an off-heap cache. This also uses sun.misc.Unsafe. There's some additional overhead. They use reference counting, and they store the size of the object on heap. So there's slightly more on-heap memory used than my pared down implementation, but not very much, only about 10%. Again, they use Google Guava concurrent LRU hash map to store the keys in. So before I proceed, just a few words about fragmentation. Now, you've probably all heard of memory fragmentation, but essentially this occurs when we allocate blocks of memory and we free them again. And this can create, if we're allocating lots of blocks of different sizes, then this can create holes in our memory space, which are sometimes never able to be filled in. So over time, we allocate lots and lots of different sizes, and we can end up with holes in our memory space, which we may never be able to fill in again. Now, word of warning, if you do off-heap allocation in the manner I've just shown you, you may experience fragmentation of the Java process, or the JVM process. If you allocate data on heap, then the garbage collector takes care of fragmentation for you. So garbage collector detects that the heap is fragmented, and it goes off and it says, don't worry about this, I'll defragment it for you. Now, in Hotspot, this is an offline process. So this is a full pause of the JVM. In Zing, for example, it's not. It's performed concurrently. But the point is, if you're allocating off-heap memory, then you risk fragmentation, and there's nothing to take care of it for you. If your Java process is fragmented, you'll probably see the virtual size of your process growing over time, so keep an eye on that, and you may see delays in performing off-heap allocations. Now, in non-garbage collected environments, swapping out parts of a process is pretty normal. So, your process gets fragmented, the operating system goes, oh, they're not really using that part anymore, I'll swap it out, and fragmentation isn't so much of an issue. The virtual size of your process grows over time, but you've swapped out the parts that you're not actually using. In garbage collected environments, swapping out parts of the heap is a disaster. If you have parts of your JVM that are swapped out, and you try to do a full garbage collection, then you'll be wishing for the days when you had 28-minute pause times. So basically, if you're allocating off-heap memory in the JVM and you're experiencing fragmentation, then you've got to hope that it's only the off-heap stuff that's being swapped out, that nothing that's backing up your Java heap is going to be swapped out. And this is difficult to guarantee. The Apache Cassandra solution, which Jonathan Ellis talked about yesterday, is to use mlock-all, which essentially locks your process so it can't be swapped out on Linux by the operating system. So what they do is when the JVM starts up, they allocate the complete heap, then they use mlock-all to lock that and prevent it from being swapped out, which is pretty clever. So their off-heap stuff can be theoretically fragmented, but their heap is guaranteed not to be swapped out. Now, slab allocation. So, what some people do to avoid fragmentation, memory fragmentation, is to use something called slab allocation. And essentially, what slab allocation does is it allocates a number of fixed size chunks. And these are typically allocated up front. So typically, for example, you might allocate a bunch of 128 byte chunks, a bunch of 512 byte chunks, a bunch of 2K chunks, a bunch of 4K chunks, etc. And objects are stored in the smallest available chunk that can hold them. So you find smallest available chunk, you put your data in there, and then when the data is freed, you free the entire chunk. Now this avoids fragmentation, but as you can imagine, it can be quite wasteful of memory. So you're not allocating just the amount of memory needed for your objects, you're allocating potentially quite a bit more. Arguably, this is just another type of fragmentation, but technically, fragmentation doesn't occur. You sacrifice, you essentially trade off lack of fragmentation for memory usage. However, this can be very good thing to do if many of your allocations are converging around the same sort of size. The most extreme example is when you have some sort of page cache in a database. All your pages are 4K or 8K or 16K or whatever. So you just allocate slabs for those. However, if you're allocating lots and lots of different sizes of objects, you might find that this is pretty wasteful of memory. One product that uses slab allocation is memcached. They used to use just standard malloc. I don't know which implementation, but apparently fragmentation was a big problem for them in the early days of memcached. So if you want proof that fragmentation actually happens in real life, talk to the memcached developers because they've clearly experienced it. So they replaced it with a slab allocator. In the Java world, HBase, for example, has a Java-based slab allocator that allocates memory off heap. So this essentially allocates a big direct byte buffer, splits this into chunks, and allows you to store data in those chunks. There are some limitations of this approach. It's pretty simple at the moment. It requires the chunk sizes to be specified up front, which makes it probably unsuitable for a general purpose cache. You need to know the sort of sizes of objects that you're storing up front. A better implementation like the memcached implementation will allocate chunks or allocate essentially lists of chunks as you request objects of a certain size. I have used this as a general purpose cache for my benchmarks. It has some limitations and there's some HBase specific stuff, but it is possible. I performed the same tests on this, and performance was pretty reasonable. It was comparable to other off-heap techniques. However, my tests were pretty artificial because I knew in advance the average size of the objects I was going to be allocated, so I just told the slab cache, hey, here's the average size. I would suggest that, I think there's a need for a general purpose slab allocator that allocates off heap in Java, so it'd be good if somebody could fork this and make a general purpose cache. Okay, so one argument goes, if garbage collection time is dependent on the number of references the collector has to traverse as opposed to the total amount of data, then storing byte arrays on heap as opposed to storing them off heap will have equivalent performance. And this seems like a fairly reasonable argument. Intuition tells me that certainly the mark phase of the garbage collection cycle is going to be dominated by the number of references the collector has to traverse. So to test this, I stored different sized byte arrays on heap. There were exactly the same number of objects stored on heap. The only thing I varied was the size of the byte arrays that I was storing. Then I invoked systemgc, and I looked at the results. I got some pretty interesting results here. The parallel collector, in other words, the standard hotspot parallel collector, seemed unaffected by the dataset size. So I imagine it's affected by the number of references we have, but as I increased the size of my byte arrays, the collection time remained constant. However, G1 did seem to be affected by the data size. So again, not just the number of references, but the actual amount of data I was storing in my byte arrays. G1 was affected by this. I would like to investigate this further. It is possible that G1 does something when you invoke systemgc that it doesn't normally do in its garbage collection cycle, like, I don't know, compaction or something like that. So I would like to investigate this further before drawing any concrete conclusions from this, but these results are quite interesting. So why store data off heap as opposed to on heap in byte arrays? Well, it may reduce your GC pause times. Again, this is inconclusive, but as I say, I'd like to perform more tests on this. But it will certainly increase the chance of you being able to perform garbage collection concurrently. And again, this comes back to the amount of free space that you have to leave on the heap. If you're not allocating large amounts of memory on heap, then you can leave less free space on heap, and you will still have the same chances of being able to collect concurrently. So that's the main reason for wanting to allocate off heap. It should also minimize the frequency of garbage collection. I've said pauses. I've said pauses and spelt it wrongly. I should have said cycles here. If you're allocating less on heap, then the garbage collector will have to run less frequently. Again, there may be other reasons, like, for example, Allocating off-heap should reduce heap compaction time because you've got less data to move around on heap. However, we have to trade that off against the possibility of off-heap fragmentation. Excuse me, just one moment. So, Terracotta Big Memory is a commercial product that provides an off-heap cache. And the key difference between this and what I've been showing you previously is that in Big Memory, everything's stored off-heap. So I talked earlier about whenever I was caching data in OffHeap Object, having to store at least the keys in my map and the wrapper objects on heap. In Big Memory, it's a cache, but everything, including the data structures that make up the cache itself, are stored off-heap. Again, we have the same limitation. Everything's got to be serialized. So again, there's a performance hit there versus on-heap stuff. The way that they implement this is that they've got a custom off-heap memory allocator. This is, I believe it's entirely written in Java. So essentially, they've written their own memory allocator in Java. And they claim that memory fragmentation does not happen. This is an exact quote. I'm not clear on how this is implemented. It may be a slab allocator. Terracotta are a little bit reticent about giving me any details of how the stuff is implemented. So I'm not exactly sure how they implement this. However, if I was evaluating Big Memory for production use, I'd want them to clarify this statement on memory fragmentation does not happen and get some answers as to why that's the case. Again, I performed some tests on this. Sim tests as before. I stored about 235 gigs of data in Big Memory, and impressively, the Java heap usage was negligible. So, I mean, I basically saw no Java heap usage at all. And I saw no old generation garbage collections performed at all in a 4-day test. So everything, I think, was happening in the young generation. Now, I haven't yet tested how much overhead Big Memory needed for storing data. Again, if I was evaluating this for production use, this is certainly a question I'd ask. And by this I mean the raw data size of the serialized objects that we're storing versus the amount of actual memory that Big Memory is using off heap. And again, if they're using a slab allocator, I don't know what they're doing, but if they're using a slab allocator, that may be significant. Again, read performance was comparable to using OffHeap Object to other off-heap techniques. My cache loading performance wasn't quite as good as other solutions. I need to do more work on this. The suggestion from Terracotta was to use bulk loading mode for this, and I haven't tried this yet, so there's no conclusive results there. But it's certainly, if you're evaluating this for production use, it's worth looking at all of these things. What's the performance of allocating objects in particular? Okay, so there are a couple of open source, I would say, off-heap storage caches. I'm just going to cover these briefly. The first one is something called Big Cache. This attempts to store most data off-heap, and it claims that the on-heap, there is some on-heap index, but it has minimal memory footprint. At the moment, there's no automatic eviction, so we'd actually need to store LRU lists, etc., on heap if we were performing eviction, which would, I suppose, defeat the purpose somewhat, but I expect that automatic eviction is coming soon. Again, I tested with 235 gigs of data. Cache population went absolutely fine, performed quite well. However, a few things. This used around 60 gigabytes of heap space. So for 235 gigs of data, I used about 60 gigs on heap. The read performance was pretty bad. It was about 1% of other solutions, and my test failed after a few minutes with an array index out of bounds within big cache. So my conclusions on this are that it has potential, certainly. It seems to have the right sort of ideas, but it's not quite there yet. Another open source solution is Apache Direct Memory. This is an Apache incubator project at the moment, and this aims to be an open source alternative to, big memory. They have written their own memory allocation routines in Java, so essentially they've written some sort of memory allocator, malloc, or a slab allocator or something, I'm not quite sure, in Java. However, the cache keys are stored on heap in a Google Guava map. So this is quite similar to, I think, just to allocating off-heap memory and storing the keys and the wrapping data structures on heap. Now, the final thing I'd like to talk about is the final technique for storing data off heap is the operating system's own cache. So operating systems, I think all of them, have their own caches for storing frequently accessed data. And you can actually use the operating system's own cache to store your data. And this is a particularly good technique to use if your data is stored in the file system anyway. And one way to do this is to use memory map files. Now, memory map files are interesting because what they allow you to do is to map the operating system's cache onto the virtual address space of your application. And what that means is that your application can access the operating system's cache directly without copying the data. So mostly when you access files, if you don't use memory mapping, you load the data into the heap space of your JVM, and you've kept another copy of that. You can use direct byte buffers, but again, there's a copy of the data. Memory map files are efficient for two reasons, because they avoid, firstly, the overhead of actually copying the data from the operating system's cache, and it also avoids double storing of data. That is, when you're storing data both in your JVM process and in the operating system's cache. So it's a very efficient way of storing data. Here's a quick code example of memory mapping a region of a file. So very easy, we use the channel.map method to create a mapped byte buffer, and then we call the load method on the mapped byte buffer. Now, the load method isn't guaranteed to load everything into memory, but it hopefully gives you a fairly good chance of loading that data into memory. And it puts it in the operating systems in Linux, the page cache. Now, the disadvantage of memory map files is that it's not possible to control eviction from the page cache. At least, I'm talking, I should have said this, I'm talking specifically about Linux here. So as far as I know, there's no way to control eviction of data from Linux's page cache. It's also not possible in Linux, at least, to control the size of the cache as well. So you're fairly limited in the control you have over the cache, and that's the disadvantage of using memory mapping. Okay, conclusions. So, first of all, I believe Big RAM is coming. Again, we'll see in 4 years' time if I owe you all that point. But I've heard, I've heard various talk about, well, in Java 9 we're going to have the ability to deal with, heaps with many gigabytes in them. I don't think that's enough. I think we need to start talking about multi-terabyte heaps. Until I hear that, until I hear people talking about multi-terabyte heaps in the JVM, I'm going to be worried. Now, at the moment, I believe Java has the opportunity to be the de facto platform for big data. And this is largely helped by projects like Hadoop and other big data systems that are developed in Java. And as a Java community, this is a very good opportunity for us, and we're on a good path there. However, I think that we need better answers regarding using large amounts of memory, and by that I mean multi-terabyte heaps, or else, people will start using C++ again. I don't know. I don't know what people will do, but as a Java community, I think we need to have better answers to this. Garbage collection is great. We're all aware of the benefits of garbage collection, and I don't want to throw that away and start having to keep track of my objects again. I like garbage collection. The good news is that the pauseless garbage collection is possible. There are implementations of it there. The bad news is that they're not free. However, I guess I'll make another prediction. I would predict that in 4 years' time, there will be a free pauseless garbage collector for the JVM. I don't know who's going to implement it. If there isn't one, then the guys from Azul can buy us all a pint. So garbage collection has limitations in certain scenarios. I've presented a bunch of solutions or a bunch of workarounds, but none of these are perfect. I do see what I've presented here in terms of allocating off-heap memory and that sort of thing really as workarounds. We can't keep serializing our objects and storing them off-heap. I mean, this is crazy. So these are temporary workarounds until we have a better solution. There may be a case for having unmanaged objects in the JVM. So in certain circumstances, there may be a case for changing the philosophy of Java and allowing people to allocate objects outside of the control of garbage collection. And just a final word, please test with your code and your data. Don't rely on my benchmarks. Thank you very much.